Good morning, everyone. Today we are going to move on to our actual proper physics syllabus. So we're going to be starting with light. We're going to do the topic of light and waves first. Alright, now light and waves should take us up to the first or second week of January. Okay, so this is going to be our topic for the rest of the term. I am loading up the handout right afterwards, so you'll give it a look. Now these little clips are going to be 30-minute blocks of classes so that we can get some questions in and whatnot. Alright, because I figure an hour of recorded video is a bit boring at times, so we're going to do them in 30-minute blocks. Alright, so let's see what we can get done this morning. We're going to start off with light. Now you all should have covered something in light in the form, in the general science curriculum, because I have seen that curriculum and it did cover a bit of it in Form 1 to 3. So some of this is going to be revision, and then we're going to move quickly forward. So let's read from the screen, starting from here. Alright, light is given out or emitted by very hot objects such as the sun or the filament of a bulb or the hot gases in a flame. It may be also emitted by much cooler materials when electrons lose energy, such as a fluorescent tube, a TV monitor, or a laser. Any object that produces its own light is said to be luminous. Alright, so once something produces its own light, as in physically produces and creates its own light, we call that a luminous object. Continuing, most of the objects around us do not emit their own light and are therefore called non-luminous. They are only visible because they reflect light from other sources. Some surfaces are better at reflecting light than others, depending on the nature of their surface. Alright, now we're going to go through this a little later on, as in how color and texture affect the reflection of an object. So let's think about some luminous objects that we should see around us. Now, I've just named a few, and then we do have some other things that create their own light. Like we have biological creatures. We have creatures and plants that create their own light, and this is called bioluminescence. So anything that creates its own life, that is alive and creates its own light, is called a bioluminescent object or organism. Alright, examples of that being fireflies. There's a couple of bugs around that do produce a little bit of light on their own. We have a lot of deep sea creatures do produce their own light. Even some plants create their own light, like some fungi and mushrooms can create their own light and whatnot. So these are things that are luminous. Almost everything else around us that we can think about that, we might consider to be luminous is not actually luminous. The best example of an object that is non-luminous is the moon. The moon itself does not produce any of its own light. The moon is just a big spherical ball of rock that is out in space. It creates no light whatsoever. Right? How do we see the moon? Is because the light from the sun bounces off the moon. Now, because the moon is light colored, right? That's why it appears to be so bright in the night sky. Okay, so almost everything, we only see things because light is bouncing off of them. If you all go in a pitch black room, take off the light, you will see nothing in front of you because there is no light. Say you have an object in a room. Alright, I don't actually know what I draw in here. Alright, say you have an object in a room and you take off the light, you will not see this object. The only way you see this object is because some light source is sending its light rays, or its light rays is reaching that object and it's bouncing off to reach your eye. If there is no light available, you will not be able to see something in the dark. All right, so this is why we cannot see non-luminous objects in the dark, because there's no light to bounce off it. So let's continue reading. Properties of light. You have to learn your properties of light. At CSEC level, we just need to know these three, but there are actually far more properties that you should know or you will learn eventually. 1. Light travels in a straight line. This has been proven without a doubt. Light only travels in straight lines. The only thing powerful enough, y'all, that can bend light is gravity. And the gravity has to be like that in a black hole or a very large star. That's the only thing that can cause light to bend. It has to be something very powerful, right, and very strong. And that's usually either a black hole, right, or a very large star. That is the only thing that can cause light to bend, because it has a large gravity. All right, now at this level, we're not going to go into this, as in this topic, how light bends because of gravity, is a postgraduate topic. It's not even a degree topic. All right, so let's continue reading. Light transfers energy from one place to another. That's how we have photoelectric cells that create electricity, because it transfers energy, and we're able to utilize that energy to create electricity. And 3, light is a wave and is part of the electromagnetic spectrum. We're going to cover the electromagnetic spectrum more in depth later down in this topic, but you have to remember light actually does travel as a wave. There are 2 types of waves that exist. When we're doing the topic of waves after light, we'll go into this more in depth. So let's look at our points. 1, light travels in straight lines. Light is often displayed as a straight line with an arrow to indicate its direction. Why do we need to indicate direction? Because light usually comes out from a light source, right, and travels in different directions. Right, so we have an arrow to indicate where it comes from, right, from the light source, and where it is going to. So that's why we have straight lines with an arrow to indicate where it is going to, or where it came from. Same difference. So we have to learn some terms. We have a ray of light is a single one line with an arrow on it. A beam of light is a collection of rays. All right, so a beam is actually, all right, a collection of rays. All right, so it's more than one ray. All right, so these are something to remember, how to illustrate, how to draw these things properly, how to write them down properly. A ray is one single line, and a beam is several lines. And we must put an arrow to indicate which direction we're traveling in. Shadows. A shadow is one of the easiest and most obvious demonstration that light travels in a straight line. When the passage of light is interrupted, a shadow or region of darkness, darkness here is in inverted commas because darkness doesn't indicate that it is devoid of light and completely black and no color and no light whatsoever. Darkness just means that the light has diminished somewhat. There are 2 types of shadows that occur. You all have to learn these terms. We have an umbra. An umbra, this is an area of total darkness, or a higher degree of darkness with well-defined edges. And then we have a penumbra. Penumbra is a partial shadow with fuzzy edges. When you all are looking at this video, I want you to go outside, right? Go outside when there is sun. It's a little bit rainy this morning. And take your hand and put it, probably I hold your hand out in midday, probably about a meter or 1.5 meters above the ground. And this is when we have bright sunlight. And you're going to realize that your shadow on the ground is going to be a little fuzzy-ish on the sides. Now, if you take your hand and bring it down close to the ground, so let's say this is the ground. All right, I'm not even going to try to draw a hand. That's just not going to be good. All right, hold your hand, all right, a certain distance above the ground, and you're going to see you're going to get a really fuzzy looking shadow. Then what I want you to do is to bring your hand closer down to the ground, all right, and you're going to get a very dark, well-defined shadow. These things demonstrate the difference between an umbra and a penumbra. Umbra is total darkness or well-defined darkness, and penumbra is a partial shadow, is a fuzzy shadow. So let's see, umbral shadow, umbra being those with sharp edges, are usually formed from a point source of light. So this is how we have to know how light behaves. You're going to have a point source. This is our point source of light. So what happens, our light travels out in straight lines from one point. Right now there are millions of rays of light coming out from any luminescent object. There are, it's not just a couple. So imagine I can fill this up with infinite amount of rays. And what happens, because light travels in a straight line, those that bounce the object here or hit the object here cannot pass through it. Alright, so let's say this is an opaque object or a solid object. Light is not going to pass through a solid object. Alright, so what's going to do, it's going to hit the wall or hit the object and not travel any further. What happens here is because no light is traveling forward, right? So this is no light is traveling forward, right? This is how we end up forming a shadow because light has been interrupted. It's not going to get perfectly dark, but it's going to see some region of darkness. And then what happens, because our light is traveling further, right? The first ray of light that passes that object is going to form the very boundary of our shadow. And then once you pass it, it's going to be bright as normal. Alright, so anytime we have a point source, this is one thing to remember. Once we have a point source, we will end up getting an umbral shadow, meaning a shadow with well-defined edges. Let's continue reading. A penumbral shadow, meaning a shadow that has fuzzy edges or a gradient of shadow, is formed from an extended light source, meaning one that is far away. When this happens, some of the light is completely blocked and some of it is not completely blocked. So let's go in here a little closer and see what's actually happening. When we have a very far light source, before we only had a point light source and there were, only small bits of light can pass. Now when you have a large light source or light source is very far, your light can travel in any direction. So not only do they travel forward, they can also travel in every single direction possible. So you see how the light here is going to end up crisscrossing? This is what's happening here. The light ends up crisscrossing as it travels through, air or space or wherever it's going. So this is what happened. The light, because it's far away, far means extended source of light, it travels, and then we're going to have all the light that hits my opaque object, right? So you see this area here, it cannot pass through this opaque solid object, right? It can't pass through it. So what happens, our first set of light that passes straight lines, so remember this is going to be, if we happen to have exact straight lines from our edge of our light source, this is going to form a pretty dark shadow. It's not going to form an umbral shadow. It's going to form a pretty dark shadow in the middle. And then how do we get these other ones around here? All right, let's just erase this. Go on next color. All right, so what happens here when the light source passes over the edge? All right, so these are the ones that are now going to crisscross. Right? Remember, just as we had before, as they pass the edge, it's going to now have a lighter shadow or the edges of a lighter shadow. So this doesn't look like this where it's one gray circle and one black circle. You're going to actually see a range of shadows. Alright, so this is what happens across here. As the light passes, you're going to end up getting your range of shadows, and in between here, what happened here, you're going to have a little bit of light that passes through because of how the rays crisscross. You're going to get a little bit of them, little bit of them. So that's how we end up getting our penumbral shadow. So what this looks like, it's really dark in the middle and then it gets lighter and lighter as it goes away. That's what happens if you take your hand and you hold it high above the ground, right? Or if you have a bright lamp at home, put your hand in front of the lamp and look at the wall. You're going to realize that you get fuzzy edges. Okay? When you do that, that's because you're actually creating an extended source, or you're blocking the light from a far distance away. So let's go back to our original size. So you have to know how to get umbras and penumbras. Eclipses, one of the biggest naturally occurring examples of shadows is seen in eclipses. There are two types of eclipses that we can experience. We have a solar eclipse. A solar eclipse is where the moon passes between the earth and the sun, thus blocking out part of the sun or all of it. And then we have a lunar eclipse. A lunar eclipse is when the earth passes between the sun and the moon, blocking out light from reaching the moon. So these happen twice a year, every year. We have lunar and solar eclipses happening twice every single year, at least twice every year. So when people say it's a really, really rare occurrence, not really. It's just really rare, or kind of rare for the place for it to occur. All right, and even that, it's not that rare. I think it's every 11 to 22 years a region will see a replacement, not replacement, or a repeat of an eclipse. So we have solar eclipses. Solar eclipses, really simple to understand. We have our sun, right, giving off light, and it's going to hit our little gray moon. We have our blue planet, because they do call Earth the blue planet. All right, this is obviously not to scale because Earth is 1,000,000 times smaller than the sun. So what happens, because of our light rays are going to pass in such a way. All right, let me draw some straight lines. I'm not going to embarrass myself trying to do this straight. All right, so you're going to have some straight lines passing. That's your straight line of your light. All right, so that's my first straight line. Let's show the next straight line. Now, when you're doing this, please use a ruler. Do not try to freehand this. We have the other straight line passing. So what happens here, this is the section, if you look here from the diagram or compare it to the diagram above, let's just make it a little darker. Can I move you? Right, good. If you look at the diagram above, where the light crisscrosses, this is where we're going to have the fuzzy shadow forming. So you see this entire area here. Let's get the marker. All right, this entire little area here is where you'll get fuzzy, or you'll see the eclipse happening. Then we have, because this is an extended source, far away source, we now have to think about the straight lines occurring. So let's look at the straight lines occurring. All right, now the straight lines will be from the top of the sun, or we use it usually from the top of the sun. All right, so that's our first line. We take the next line from the very top of the sun, and we cross it, straight lines. All right, now if you all look here, this is the same equivalent as at the top here. This section here is the very same equivalent as all here. So what's going to happen? This is the section where we have a total eclipse happening or a dark eclipse happening. This section here, you see how small this is compared to the rest? Right? And this is usually like a big circle. Imagine it's a big circle, and just in a little small piece in the middle, you see a total eclipse. A total eclipse is where the sun is completely blocked out by the moon. And depending on how close the moon is to the earth at the time, sometimes it gets as dark as night for a couple of minutes. All right, so that's a solar eclipse. Again, it happens twice a year, or every 16 months, twice every 16 months, all right, every year for the last, how old is the moon and the sun? Probably 3.4 billion years. No, I lied. I'm sorry. 4.36 billion years. All right, we've been seeing solar eclipses. The planet has been seeing eclipses for 4.36 billion years. So it's not to say it's something that very rarely happens. It's not to say it's something that's ominous and weird. All right, it happens a lot compared to this age of the Earth. And when we have a solar eclipse, not solar eclipse, a lunar eclipse, it's just a little different because what's going to happen, the moon is now behind the Earth and it's going to get blocked out by the Earth. So the Earth is going to block the light reaching the moon. This is a much simpler one because the Earth is so much larger. The Earth is 3 times larger actually than 3 times or 6 times? 6 times larger than the moon. So let's get rid of these lines just so I can try to freehand a little bit. So what's going to happen? You just draw your straight lines across and the light coming out from the sun hits the Earth. And what you end up getting, you're getting a very large area where the moon passes into the shadow of the Earth. Usually when a lunar eclipse happens, half of the planet sees it at a time. Or at least 1/3 of the planet will see it. When it comes to solar eclipse, is much less. Alright, much less. So let's just continue down. Light transfers energy. Light is a form of energy. And it is made up of tiny particles called photons. These photons travel very fast and therefore takes energy with them. We will look into see how a moving object has energy when we start doing mechanics, and that will be next too. Light is part of the electromagnetic spectrum. The electromagnetic spectrum is a collection of waves that transfer energy from one place to another. The entire spectrum is made up of 7 broad regions. All electromagnetic waves travel with the same velocity in the vacuum of space, and it's the fastest anything in the universe can travel with naturally. We're not talking about if we speed it up or we run through some synthetic methods. Anything naturally traveling, the universe has a constant, it has a limit, and that is the speed of light. Is the fastest anything can travel in this universe. No, we cannot travel at the speed of light yet. Our technology isn't quite there. All right, we're still a good distance away from traveling at the speed of light. So just to tell you all, you're going to have to learn this value eventually. Not today, not tomorrow. We don't really use it right now, but you're going to have to learn it eventually. And luckily, they do give you these values in exams. So what is the speed of light? The speed of light, let's read this, is 300,000 kilometers. It travels 300,000 kilometers in 1 second. So if I had a distance of 300,000 kilometers, that light will travel that distance in 1 second. All right, that is how fast light travels. Okay, so the constant or the symbol that represents the speed of light is a common c, and c is 3 by 10 to the 8 meters per second. All right, this is a number you have to remember, or it's 3 with 8 zeros behind. See why we do standard form? Because it's easy to get rid of these, to mix up these zeros. So it's 300 million meters in 1 second. That is how fast light travels in the vacuum, the emptiness of space. I am going to give you a little bit of homework to read up on the pinhole camera. Alright. Oh, heads up, it could be an assignment. Alright, so I want you to read up on the pinhole camera because this is also a demonstration, alright, on light traveling in straight lines. Okay, so we're going to wrap up here. So we just went through the very basics of light. We looked at what a luminous object is, what a non-luminous object is, our 3 properties of light, which are light travels in a straight line, it transfers energy from one place to another, and it's part of the electromagnetic spectrum. I'm just recapping what we did today. Light travels in a straight line. The best demonstration of light traveling in a straight line is the formation of shadows. Alright, so we have two types of shadows. We have umbras and penumbras. And then when we want to look at big examples of shadows, we have eclipses. You all have to know what's the difference between a solar eclipse and a lunar eclipse. Okay, and then the last one here, we have light travels as a form of energy, and we know the speed or the velocity light travels with, which is 300 million meters in 1 second. So that's it for today. Tomorrow, I'm going to post these up quite often actually, so we can get this done in small little batches. So we're going to have you all to read up on the pinhole camera. We could or could not have it as an upcoming assignment, where you're going to have to build something, right? It doesn't matter to me whether you're home or not, you're going to build a pinhole camera. So read up on it, so it's not going to be so hard. The most things you're going to need for pinhole camera is a shoebox, or cornflakes box or something like that, and some wax paper. Right? If you don't have wax paper, everybody should have some wax paper at home. Alright, so that's it for the day, everyone. Give us a look if you want. I am posting up the handout. Next day, we will go on to the laws of reflection and refraction. Right, and go through that. This one is a bit lengthy because there are some equations here that we have to know how to use. Please note we are going to do a lab both in school and at home with the laws of reflection. So I'm just giving you a heads up. You're going to need a mirror and some head pins to do this. Alright, so everyone have a good day, and I'll see you all next time. Bye bye.